What's going on here? Uh, Okay, so first of all, um, we have a quiz on Friday.
Probably cumulative test, not just like on ranking the cycle.
Right. Yeah, these are all cumulative, so go back through all your notes. And then the final is on Wednesday of finals week. That is the 16th, I think. What's it? Today's the 10th, right? So that must be the 17th.
Yeah.
Okay. And it is from 11 to 1, and it's not in this room. I don't know why they started doing that differently. So it's the floor below in 1724. So down the stairs, somewhere right in this area, though. Um, and we'll see what we covered today, see what problems I assign. I don't know exactly what this will go up through yet, but it's going to be a cumulative test, so it's going to be cover everything that we've done up until this point, at least. Um, Anybody have any questions about either of those? All right. Well, so let's go back. We did some work on this problem last time. So we're going to do this, and the thing that we didn't do was part D before. Well, we didn't get any of the answers, so let's just go through the whole thing from where we are now. So we figured out that we went through all this process. Uh, we figured out that H1 is 2793 times 10 to the third.
Were you using like tables for that versus the Wisconsin priority websites?
Why did some of the numbers not match up exactly?
Not exactly online, just slightly off.
Yeah, that's probably what it is. I probably got those numbers, did those numbers last semester with a table. Uh,
Professor,
yes,
I have a small question about the final. So you said we won't need to like take the values from a table on the final?
right.
Okay, thank you.
Yep, I'll just give you values.
Or we figure them out.
Well, you won't have a computer. Well, yeah, I guess if you're going to use like an incompressible approximation or something, you can sometimes figure that stuff out. Yeah, that's right. So that was H1. H2 is 2006.7. H3 was 173.8. And H4 was 189,792. Okay. So that is 189, let's call it 0.8 times 10 to the third. So that's the first step in all of these kind of problems. Now we're going to figure this kind of stuff out. So the net power developed. And we're given a mass flow rate. So the net power developed. Can anyone off the top of your head come up with an expression for that? Like, think about what the meaning of that would be. Like, where do you get power from? Where do you spend power?
The turbine minus pump.
Right, exactly. So this would be WT dot minus WP dot. And so we can think of this as M dot times WT dot over M dot minus WP dot over M dot. And now let's think about the meanings of these. So in the turbine, remember that. So we're going to go through this whole thing. That's going to look something like this. In turbine, there's no heat exchanged. So you have negative W for the control volume dot plus M dot times the quantity H inlet minus H exit. So that's what you get when you simplify the first law for control volumes. And now we have to think about does the sign change or stay the same for work in a turbine? So in a turbine, we're getting energy out. Is that the same sign convention, as the first law sign convention, or the opposite?
If work is being done to the surroundings, that means that work would be
Positive, right. So we're going to keep the same sign here when we change this to W turbine dot. Are you with me on that thought process? Look, you can also just, I don't know why I said look like that. You can also just go back to the equations. They'll be given on the test. But in a lot of cases, you can just sort of think this stuff through. So we have negative W dot for the turbine plus M dot. What state is the inlet for the turbine?
superheated vapor.
That's the phase, but of the four states, which is this going into the turbine?
State one.
Right. So this is going to be 1 minus 2. And so WT dot over M dot is equal to H1 minus H2. All these four lines were sort of unnecessary. I could have, if I knew where in my notes exactly those equations were, I could have just gone back and looked. And so this is equal to, now we have these values. So 2793 times 10 to the third. Minus 2006.7 times 10 to the third. So that is 786.3 times 10 to the third. And now we have to do the same thing for WP dot over M dot. By the same reasoning, I mean, all that's going to change is so let's start with this. So we have 0 is equal to negative W dot for the control volume plus M dot times the quantity HI minus HE. Now for the pump, is energy through work coming into the system or leaving the system?
Going
Into the system. So is that the same or opposite sign convention as the first law? Opposite. And so in this case, you can think of this as, so 0 is equal to positive W dot for the pump plus M dot. And now what's the inlet of the pump? What state is that? Yep. Exit is H4. And so we can write this as WP dot over M dot is equal to, I have to switch the order this time, so this is H4 minus H3. With me on that? And then, so H4 is 189.8. H3 is 173.8. So that is 16. This is our expression for the net power developed. So we're going to go, so the net power developed is M dot times 786.3 times 10 to the third minus 16 times 10 to the 3. And we're given that M dot, 120. And the answer is 9.24 times 10 to the 7 watts. How many watts does our body consume? Something to just compare this number to. That's a super big number, Like, is it half a watt per second, or, a millionth of a watt per second or whatever? So,
I think there was like an inaccurate number in the Matrix when they were being used as batteries.
oh, was there? That's funny.
That was the whole point of the movie, that humans make good power sources.
Yeah, right. That's funny. I'd never thought about that. Well, 2,000 calories is 8 million about joules. So 8 times 10 to the 6 divided by, so there are 24 hours, and then 3,600 seconds per hour. Okay, so about 93 watts. That's about what our energy expenditure is.
Google says about 100, so you
Yeah, right.
more accurate.
Yeah. That's a lot, actually. Anybody here?
power light bulb.
Yeah, well, I was going to think so, I mean, I have at various times, tried to ride my bike as fast as I can. I never was very fast at it. But I mean, when I was in good shape, riding about as hard as I could for like an hour, I could make power my bike, let's say 220 watts or something, So That's only like that's really not that giant of an amount of wattage compared to what my body's burning just sitting around. That's discouraging.
It won't be like a wattage of, I don't know, small scale power plants or something like gigawatts.
I really don't know, actually. That's a good question. I mean, I think these problems are designed to give you numbers that you would see usually. So I don't know. So let's say it's that 9 times 10 to the seventh watts. Um, okay, so now the rate of heat transfer passing through the boiler in kilowatts. Um, so
92.7 megawatts is the typical capacity of a small to medium sized power plant or a very large wind or solar farm.
okay,
So
so you'd need 1 million people in your human battery farm to to be the equivalent of a small.
it can power an estimated 400 to 900 average homes.
Okay. Okay. 92. It's exactly 1 million times the rate of a person. That's amazing. Uh, so now we're going to the rate of heat transfer to the steam passing through the boiler. So we're looking for this. And we're going to calculate that as m dot times qh dot over m dot. And now we're going to think about the signs of this stuff. The first law for control volume simplifies to this. In the boiler, there's no work. So we just have this plus m dot times the quantity hi minus he. And at the boiler, heat is entering our system. Does that match or is that opposite of the sign convention for the first law?
The heat is entering the boiler, so it's positive, right?
It's positive, so it's the same sign convention. Yep. And so this is going to be QH dot plus M dot times entering the boiler is state 4, exiting is state 1. And so we have that QH dot over M dot is equal to H1 minus H4. And again, you can just look that up in your notes. And so H1 is 2793. H4 is 189.8. So that is 2603.2 times 10 to the third. And now QH dot is just this value times the mass flow rate, which was 120. So that is 312.3.4 times 10 to the third. watts. Does that make sense? No, not really. What is going on here? Oh, because I didn't, yeah, it's to the 6. Okay, that makes more sense. Times 10 to the 6. So this one, let me just make these match. I'll call this 92.4. Okay, so we're pumping a lot more heat in at the boiler than we're getting out of the plant as work, and that's just the nature of entropy and stuff. Any questions about that one? Once you sort of see the flow of this, all these questions are kind of the same. The thermal efficiency,
We're using the one where it uses the specific enthalpy or the change in temperature. I think there was like two different ones in the thermal efficiency and one ideal version.
well, remember that, well, we're going to use the one with the enthalpies because that's just how to always think about it with this stuff. But remember that for this ideal Rankine cycle with only isobaric processes and isentropic processes, remember that this is an ideal power cycle. So those will match each other.
If you were to like use the properties tables to figure out the temperature,
Exactly.
still be
They'll match. Exactly. Yep. Everyone with me on that? Follow what I'm saying? This is everything that we've done so far is a perfect cycle. And so it has to match all of the things we have for ideal efficiencies and stuff, everything we've talked about. But yes, that's another good point is like, yes, we could use that, but we'd have to go back and find the temperatures and stuff. We already have the enthalpies. So this is, well, let's just go through. I started down this road of sort of reasoning these values out. You can do that with all of this. Let's do it again. So the efficiency is the work done by the turbine minus the work used by the pump divided by the heat put in at the boiler. And we have expressions for all of these things. So WT dot over M dot was H1 minus H2. Well, let's just put in the value we have. So 786.3 minus the value for the pump, which was 16 times 10 to the 3. Divided by Q dot at the boiler, divided by M dot, which is 2603.2. All those times 10 to the thirds cancel. And we get an efficiency of 295.9, 296.296. Well, that's depressing. I mean, look at how low that is. That's the efficiency. That's how much work you get out of the heat you put in. Like that heat is hard earned, and then that's how much benefit you get out of it in work.
When
And this is an ideal power. This is with no inefficiencies at all. No, no irreversibilities.
Like natural gas and coal and gasoline, they all have like a lot of energy.
Yeah.
Like a lot of watt.
Right. That's right.
Numerically wise.
Is it
Right.
their capacity to like burn really hot that increases their efficiency for?
Yes, you get better efficiency if you can increase the temperature and or increase the pressure in the boiler.
So maybe like, I don't know, increase like the amount of fuel that you're burning and just thicken the walls so they can hold that.
Yeah, so that's the kind of thing that's worth thinking about. One thing, I don't think I mentioned this yet, while we're thinking about, sort of practical considerations. So you'd really like to have a super high temperature and a super high pressure in the boiler. But remember that a super high pressure increases the boiling point. Okay? So, which means that if you increase the pressure a lot, as stuff comes out of the turbine, it's also going to have a higher pressure as it comes through the turbine, you're going to have more liquid in your mixture. Okay, can you see what I'm talking about? Because you might still have a very high temperature, but it takes a higher temperature to make it a vapor, which means that you're running liquid through your turbine blades. And one practical consideration is that your turbine blades are going to break down a lot more, So there's all these like complicated interactions. Like you can't really think through like one thing makes this better because there's these other things that happen as a consequence,
You have to use like what differential equations to map out like several
Yeah.
different variables.
Right.
To find the
Yeah.
sweet spot.
Yeah. And the same thing with a supercritical fluid, like you think like, oh, let's just keep going with the temperature and pressure until like past the critical point, and then that'd be really efficient. It would be really efficient, but that's even harder on turbine blades.
And dealing like with fluid dynamics would I don't know Nova Stokes kind of factor in that. That's like really really complicated to work out precisely because of all the
Yeah, it's very right. Yeah, the Navier-Stokes equation. I mean, yes, all fluid mechanics has, can be solved using the Navier-Stokes equations. They're really complicated. But I think, so I guess if you're going to try to model, mathematically model what's going to happen as your fluid goes through the turbine blades, then yeah, you'd have to do very complicated computational fluid mechanics. And I'm sure they do that, I'm sure they do a mix of experimental stuff and mathematical stuff. Experiments can get really expensive if you're breaking expensive equipment. Calculations can get really expensive too, especially in fluid mechanics, because they're not hand calculations. And so you're buying supercomputer time and stuff like that. In my department at the U of Minnesota, I was a solid mechanics person, but half of our department was fluid mechanics people, and they use tons and tons of supercomputer time in their research.
And you have to like rent those out for costs.
Yeah, or the school can buy it, I guess, but yes, it's expensive to use that stuff. You have to pay for time.
How powerful were the computers?
I don't know. I don't remember. I think I did at times hear values. They were, it was much bigger than what was available. I don't know how it would compare to computers now, to be honest. I mean, that was not that long ago. I guess 20-ish years ago. But I don't know I'd be interested to know how those back then compared to what you have sitting in front of you.
Like the mainframes and the 70s or 80s.
Yeah.
Like now a smartphone is more powerful than
Yeah.
that. So
right. Yeah, that stuff is amazing. And then I don't know about the 70s, but mainframes even still into the 60s, I think, used vacuum tubes. I don't think they had I don't think they had transistors working well yet in the 60s. And so that stuff was very expensive, very fragile. Um, my first computer was, I remember I remember going to the store to buy it. My dad being like, you guys, this is not a toy. This is like serious. Like, don't mess around with this or whatever. But it was a Commodore 64. So it had 64K of RAM. And
That was good back then.
and zero. It wasn't great, but it was like affordable, you know. It was pretty cheap. I think it was only $200. I mean, you know, money was, there's been a lot of inflation since then, but um, it was $200. Uh, you used the TV as a monitor. Like you just unplugged the TV and plugged in the computer to use it. Um, and you could program BASIC on it. There was no hard drive. Everything was just stored on, we stored stuff on cassette tapes, like magnetic tapes that looked like cassettes. And it had a lot of cool games.
Was Tetris a thing by then, or?
No, well, I don't know. No. What year would that have been? I think maybe Tetris, I seem to recall Tetris started in 1985, which was around that time, but we didn't know what Tetris was. It wasn't on there. Okay. So that was C. And now finally, we're on D, the one we've been waiting for. So now we're going to try to figure out the we're trying to figure out the mass flow rate of the cooling water. And we are given that it undergoes a given temperature increase and there's negligible pressure change. So if you remember when we did it last time, we assumed that there was no pressure change. So let's just sort of sketch out what's happening here. Here's the condenser. We have the working fluid going this way. If you think of it as this of like a blown up picture of the diagram of the cycle. And so this is the mass flow rate of the working fluid. And then we have the cooling water going this way. And we're going to assume that it's steady state. Okay, you guys would have come up with that one. I have no doubt. What are some of the other assumptions that we're making here for this condenser? Before you look at it, try to think of it. What? No work. That's right. It's rigid. Then there's the one that's kind of surprising at first thought because, I mean, the whole point of this is heat exchange, but there's no heat transfer because all the heat exchange that we're discussing is between these two streams of fluid. There's no heat transfer from inside our system to the surroundings or vice versa. So Q dot is 0. Then there's the ones that we always pretty much use. We're not going to worry about changes in kinetic energy, changes in potential energy. Okay, and this just said, so, and we're also going to assume that everything is incompressible. Actually, let me be careful about that. Though the cooling water is incompressible. We're not going to have to assume that the working fluid is incompressible, which is good because in the working fluid comes into the condenser as a vapor. or is largely vapor. And then we're going to assume that delta P is 0. Okay, so let's start putting together the first law for control volumes. So
would the delta P equal to 0 tie into the rate of work for the control volume? Since there's no pressure, there is no work. Or are those like can those be mutually exclusive?
those can be mutually exclusive, like, so there's no work of expansion because it's rigid. So the volume isn't changing. But if, you could have a rigid container and change the temperature of a gas and it would change the pressure. Um, uh But I guess actually I don't know. So let's start thinking about the first law. Steady state says there's no change in energy. There's no heat transfer or work. So I'm just going to have m dot steady state. So just m dot times h inlet minus m dot times h exit.
Would it be in the inlet being state 3? Would the inlet be state 3?
So, and now I'm going to break this down. Um, so first thing is this is m dot for the working fluid times h for the working fluid at the inlet, plus same thing for the cooling water. Then minus both of these for the working fluid and the cooling water. And so now I can write this as, I guess I'll think about combining those two terms for the working fluid. So we have m dot for the working fluid times, so now let's think about that. For the working fluid, going into the condenser is state 2. So this is H2. Leaving the condenser is state 3. And then we have m dot for the cooling water times H for the cooling water at the inlet minus H for the cooling water at the exit. This is all stuff we have. So m dot for the working fluid, was that the 120? Yes. So we have 120 times H2 minus H3. H2 is 2006.7. Times 10 to the third. H3 is 173.8. And now I'll just write these, now that these are all numbers, I'll just change this notation to this. We're trying to calculate that m dot. We can calculate that m dot if we know what that difference is between enthalpies at the inlet and exit. So how are we going to get that? Anyone remember how we approached that in class on Monday? So remember that this cooling water is incompressible. That's an assumption we're making. And so for the cooling water, delta H is equal to delta U plus delta PV. P is constant, that's given. V is constant because this is incompressible. And so this whole term goes away. And so delta H is equal to delta U. Well, for an incompressible material, we can write that delta U is equal to C delta T. C for water is 4186 in SI units. Delta T was, I think it said it was an increase of 18 degrees Celsius. So that is 75,348. And that is our, this is, remember we need to go from inlet to exit. So this is actually negative. This is negative, and that is our HI minus HE. And that all makes sense because then when you move this stuff to the other side of the equation, you get that m dot times 75,348 is equal to 2.20 times 10 to the 8. And so m dot is equal to 2919 kilograms per second. So about 20 times as much water going through the radiator as cooling water compared to the working fluid moving through the system.
In actual power cycles, do they just keep it at room temperature when they and just increase the amount of fluid going through the control volume, or do they try like lower the temperature? Or
my only so just full disclosure, my only knowledge about real power plants and stuff comes from the problems that I've done. And I think in textbooks, they try to make those somewhat realistic. So let's see what the temperature is in this problem. I really don't know the answer to that. I would think that you don't make an effort to cool stuff down because cooling stuff down takes a lot of energy. It's expensive, So my guess is that they deal with very high temperatures and sort of standard atmospheric temperatures. But let's see what it is for this. So coming out of the condenser, that is our that is our 3, and so 8 kilopascals and 173.8. So the pressure is 8, and the enthalpy is 173.8 kilojoules. And so, yeah, that's 41 degrees Celsius. Room temperature is about 22 degrees Celsius. So that's still pretty hot, you know. And it's a very low pressure. Any other questions? Okay, well, that's it for today. I will talk a little bit on Friday about the main thing I want to get to is I want to talk about, so far everything has been perfect, perfectly reversible. That's not realistic. So how would you go about including some irreversibilities into these calculations? So I want to make sure we get to that on Friday, and then we'll see what else. Yeah, so